And finally, I'll just hide the controls. Good. Okay, find an equation of the tangent at a particular point. So there's no point sketching or anything, is there? We just know what they're talking about at any particular point.
Yeah.
Which is 1 and -2. Let's find the equation. And so, of course, that equation being in the form, well, y equals mx plus c is the form that I would use first of all. We'll look first of all for the what of the equation.
Yeah, cool.
So what part of the y equals mx plus c shall we look for first?
What the gradient is.
Exactly. For which we shall use what method?
Is that just
in order to find m, the value of the gradient is
wouldn't we use implicit differentiation together?
Exactly, yes. So we've got y values equal to that, and we can say, well, let's try and I beg your pardon. That's why it's implicit. That's what I mustn't say. Didn't think. This is implicit differentiation. The very point of it is that we can't say y values equal to a function of x explicitly. We haven't got an explicit statement of y as an explicit function of x only. It's only implicit. We could possibly make it explicit and make y the subject, possibly. That would be one way to do it. It's just needless hard work when we can differentiate implicitly and then get dy dx explicit.
Right. Okay, cool.
So, starting with 2x squared plus 3y squared minus x plus 6y plus 5 equals 0. So let's take them term by term.
All right, cool. So 2x squared just goes to 6x. Wait, no. Oh my God, 4x.
4x, yeah. Fine.
Goes to 6y.
Oh, perhaps you're looking at this one, which is, what's this going to be?
6y, but is it?
But you're right. But there's a bit more.
Don't you have to times it by don't you have to times it by like 2x squared or something?
Well, not that. What you want to times it by is the derivative of the inner function of this.
Oh, okay, right. So it's times by 4x.
No, the inner function of this composite here. So think of 3y squared as a composite function. 3 times the square of y, where y is an inner function of x itself.
Okay.
Now, in general, when you're differentiating a composite, so you've got y of u of x. So you've got an inner function, which we often call u. You know that dy dx is given by what formula?
dy by dx is given by, like what, dy over.
We differentiate the whole thing as though the variable of differentiation were the whole of the inner function, as though u itself were the variables. So we differentiate with respect to u, dy du.
Oh yeah, sorry, yeah. Oh, I didn't see the u. That's my fault.
Oh, the u here.
Yeah. I think I can move this. Right. Yeah.
So dy dx equals dy du times.
Dx du.
Other way round, although
du dx.
We do jiggle them about, you flip them and things. That's true.
Right. Yeah. Okay. Du dx.
But when you're doing stuff like this, There's no need
Yeah.
to write out u and stuff. You just say
Okay.
to yourself, okay, well, I'm differentiating first of all with respect to the inner function, which in this case is y.
Yeah.
That's a bit confusing because the outer function is 3 squared of stuff,
Yeah. Okay.
not y.
Right.
We'd have to call that something else, like z equals
Okay.
3y squared. So with respect to y, we would say that dz with respect to y were, what would that be? Well, it's what you said earlier.
6z.
Except y.
6y.
So 6y, yes, but the chain rule here tells us, which is the rule for differentiating a composite function, isn't it? The chain rule is composite function. It's the composite rule, really. The chain rule is telling us to multiply the result of that, 6y, by the derivative of the inner function, du dx, which in this case would be what are we multiplying 6y by?
So 4x.
Oh, you keep looking back here to this one.
Yeah. Yeah. Sorry, is it
Which,
just
that's a separate.
oh right, it's y. It's literally just like dy over. Don't you write it as like you're right, it's like dy over dx.
Well, what is, you see, what we're saying is, what this rule tells us is that if you've got a composite function, you've got y as a function of something else, which is itself a function of x. You first of all differentiate with respect to the whole of the inner function. So you differentiate y with respect to u, and then you differentiate the inner function with respect to x. Now, what's the inner function here is y. And what's the derivative of that with respect to x?
Dy over dx.
Exactly. So this is how we start arriving at what we want, which is dy dx. Even though we didn't have y as an explicit function, that was definitely a mistake writing that, I wasn't thinking. Even though we don't have y as an explicit function of x, we differentiate implicitly. We differentiate the implicit function of x with respect to x all the way through using the chain rule where necessary. Okay, but this one is completely separate from here, and then we're going to do that completely separately. When you've got one thing plus another minus another, differentiating is completely term by term. You know, you just separate it into separate problems. Derivative of 2x squared is 4x, good.
Yeah.
Plus the result of differentiating this, which is that.
Okay, cool.
So now we carry on.
-1.
Good.
Then you do it as 2 separate parts there. So
yes, we
be
need to, yeah.
6 times dy over dx.
No, what we'll do is say product rule.
Okay.
You know how the product rule works?
I actually can't remember.
There's a formula for it where we use u and v, but I prefer not if possible, because it's only describing a fairly simple logic. You differentiate one of them and leave the other alone.
Right.
So in this case, it would be the derivative of 6x is...
yeah, 6.
Oh, sorry. But that's times y.
Yeah.
So differentiate that, leave that one alone, but you've got that product there. And then do it the other way around. You say plus, leave that one alone and differentiate that, and you've got
6x. Or is it just x?
No, it's 6x.
It is 6x.
It's the whole of that part of the product. I mean, I've passed the product 6xy in that way when I could have done it as 6 times x times y. And then I could have left the 6 out of it, really. But I put the 6 into that x bubble.
Right, okay.
Then I'll treat the two bubbles as 6x on the one hand and y. Could have put the 6 in the y bubble if I liked. It's not going to make any difference.
Okay.
Okay, but what we've got here then is 6x differentiating to 6. And then I leave the y alone. And then 6x left alone. But now we need to differentiate y. You see what I mean?
So, yeah.
So it's the first one differentiated and the second one left alone. And now it's the first one left alone, but now we need the second one differentiated.
Okay, cool.
With respect to x. So what shall I write here?
Oh.
If I've got y up there.
So just, I was thinking 1, but that seems.
With respect to x, though, isn't it the same question we had here? Where for
dy over dx.
That's right. Again.
Yeah. Okay. Okay.
So this is fairly typical of what will happen when you differentiate implicitly. You may end up with more than one mention of dy dx. So we're going to need to solve and make dy dx the subject to get an explicit derivative.
Cool. Yeah.
What next?
And nothing. Well, equals 0.
Plus 0 equals 0. Yes, quite. Because the derivative of 5 is 0, and so is the derivative of 0 equal to 0.
Yeah.
Great. So now we just need to make dy dx the subject.
So we have to. Ooh. Okay, so that seems fun.
What would be a good strategy?
Make dy dx the subject.
Collecting terms?
Yeah, move 6
terms on one side and everything else on the other.
Yeah, so move 6y times dy minus dx over. Actually, do we want to move that over? Because that's all going to be negative. Yeah.
I mean, we've got everything on the left at the moment, and our dy dx terms are positive. We may as well leave those on the left.
Right, yeah.
You think?
Okay.
6y times dy dx plus later on 6x times dy dx.
Yeah, okay.
Equals what?
The rest of the equations. So, minus 4x.
Yeah.
Plus 1.
I'll put the 1 first since it's positive. Minus 4x.
Minus 4x, yeah. Minus 6y.
Yeah.
That's it.
And that's it. Good. What next?
So you can't really divide it by 6x and 6y, can you?
You nearly. You can, as when you've done what crucial move?
Can you?
Can we turn 2 mentions of dy dx into 1 mention, which is where we're going, isn't it? We're trying to get it.
Oh yeah, because you could add them.
Yeah.
You could do.
Yep.
Can you put 6y plus 6x and then brackets?
Exactly.
dy dx.
Yeah, I'm going to put that first.
Cool.
Open the brackets and do.
And then and then you divide both sides. Okay.
Exactly.
Cool. And divide the other side by 6y plus 6x. Do they expect you to go any further? No, they don't.
Yeah, sometimes. Other times not.
Okay.
This doesn't look like.
Yeah, it doesn't look like that's very nice to divide. Okay. Cool.
So what next?
What's the question?
Where were we? We wanted to differentiate, get dy dx y.
Yeah. We have successfully differentiated.
Yeah.
So find an equation of a tangent at point 1 minus 2. Okay, so we have a derivative. And then So we could put the x's on. Wait, find the equation of a tangent. So to work on tangent, that is that's just like
It's going to have a straight line equation, isn't it? The tangent.
yeah. Oh yeah, of course. Right. So oh, but that's the derivative. Oh, but that was the original.
Do you remember why we launched on this mission to find dy dx?
Was that to find the gradient?
Yeah. So
right.
Dy
So
dx in general equals that. We can say m, the gradient of our tangent equation at that particular point, is going to equal
1 minus 4x minus 6y.
Where x and y are equal to
1 and minus 2. So 1
yeah.
minus 4 is minus 3.
Yeah, exactly.
Plus 12 is 9. It's 2 negatives. Yeah. 9 and then 6 times minus 2 is minus 12. Plus 6 is minus 6. So the bottom's minus 6 and the top is minus 3 plus 12, which is 9.
Yeah.
9 over minus 6. That is the gradient. So I mean we could just leave it as that.
The gradient, yes.
Oh yeah, true.
It does cancel down.
Yeah.
Good.
So,
okay, and then what?
Find the equation of a tangent. Well, we have 2 points. Would you put it into like y minus y1?
Yeah, if you must. I mean, sorry to be flippant about that particular formula. I tend.
Yeah.
I much prefer y equals mx plus c myself.
That's fair enough. We can. Yeah. Actually, that's completely fine. Yeah. Y. So y is minus 2.
Yes.
I think we just use it.
I would say in general we know this much. We've got y in general equals minus 3/2 of x plus c. And then we could say in particular, one particular example we've got is that minus 2, I would even put e.g. really, just equals that fraction of an x value of 1 plus c.
Yeah.
And then solve c from that.
Right, yeah, okay. Minus 1/2.
So minus 2 plus 3/2, basically.
Yeah. Okay, so and then y equals mx plus c, which is x plus oh wait, minus. Oh I wrote the c value in the end spot.
That
was a bit silly of me.
Can't quite see what.
There we go. Yeah, I have the yeah. I've got the same as you. Yeah.
Are we agreed with the
yeah
gradient and y-intercept? Good. And then we just have to put it in their form: ax plus by plus c equals 0, where a, b, c are integers. So we just get rid of the fractions here.
Yeah. So times everything by 2.
Absolutely. And then you get 0 on the right-hand side. So, and alphabetical order as well, I suppose.
3x plus 2y plus 1.
Yes.
Equals 0.
Excellent. Right.
Nice.
So that's fairly typical of implicit differentiation for a typical reason of using the gradient function to find a particular gradient.
Cool.
Because the derivative is the gradient function, giving you the gradient at any point along the curve. Fine. Right.
Okay,
cool. Yes, this one looks a bit different, so let's try it. Yeah. Right. 1. Damn. Right, here we are. Find the exact value of the gradient at the point on C with those two coordinates. So yeah, a bit different, but similar principle. So going through, the other time we had it 0 on one side of the equal sign. It doesn't matter how it's arranged in that respect. Just term by term differentiate with respect to x. Now this will need a bit of processing there to know how to differentiate 3 to the power of x. Ooh, that's a bit of a puzzle in itself.
So it's, if you're differentiating, you're just lowering the power and timesing it by the old one. So are you allowed to write 3x to the power of x minus 1?
I'm afraid that's a very different animal to x to the power of something.
That's cheating, okay.
Yeah, it's just a different problem.
Yeah.
X cubed and its ilk. I mean, there would be different approaches. I think what I'll do, what I'll suggest is use e and log base e as cancelling each other.
Okay.
So what about log of e? So if you have, you know that logarithm to a certain base, I mean, if we say log to base 10 of 1,000,
yeah.
what would be? And how would you think, what's log to base 10 of 1,000? Have you got a useful form of words for that? Like the definition of log? A good way to read it is...
Oh, it's 3.
Yeah. Yes, well done. Because it's the power you have to raise 10 to get, isn't it?
Yeah, yeah.
Yeah. Well, the same with natural log. It's the power you have to raise e to get. And therefore, if you follow it with... sorry, I should have made the point with log 10. What about the power you have to raise 10 to get 10...
What is in it's just 10? Oh, 1.
Yes, and then if it was 10 to the x, these would cancel, wouldn't they? The power you have to raise 10 to get 10 to the power of x,
yeah,
would be what?
X. Right.
Yes, exactly, because it's sort of
right.
It just is the power that you're having to raise 10 to get 10 to the power of x. It kind of, it's obvious, but also mind-bending.
Yeah, okay.
But by definition, you can kind of get there. Is that where I'm trying to get here? I'm just wondering. Or should I be doing it the other way around, doing e to the power of log of something? Can't quite remember. So the point is that these cancel. Therefore, I can rewrite x like that. So therefore, I can rewrite 3 to the power of x. I mean, I could just take logs of both sides as well, but I won't. I'll just deal with the left-hand side. Log of, I'd rather write, what about that?
Okay, so I look at it at the top there, which is...
So that's fair enough, isn't it? E raised to the power, which is the power I have to raise e to get this stuff.
Yeah.
Is that stuff.
Right, okay, yeah.
I lost track of that myself while I was saying it, but it would, I think it's, you know, it is logical. But if you can at least see that those two are just cancelling like that, therefore we've got 3 to x.
Okay, cool.
Well, that should work now, in that we can, if we rearrange that, and expand, I mean, because we can rewrite this much, can't we? according to that rule, really, because
Right.
different rule. But how can we rearrange log of a to the power of b in general? You know that log mechanical rule?
Equals c.
Well, yeah, but how can we just simplify that, expand that expression?
Oh,
For example,
well,
if you've got log of a squared,
yeah.
then you might think of that as log of a times a.
Right, yeah.
And then you could
Okay.
expand that how?
Okay, so yeah, expand that out to log a times log a. Wait.
So in general, how can you expand log of a times b, for example? So if you look at that as a special
Oh,
log
as
of a
in, ln. Oh, I'm thinking of the same thing again because b's not defined.
See, log of a times b.
Yeah.
And to explain this, you'd have to go back and look at powers, but it is worth doing.
Okay.
But if we just skirt the issue for now, do you know the mechanical rule? Log of AB expands as...
Oh, is it? Oh, it's one really long. It's like, and then...
It's because we're talking about powers you have to raise, say, E to.
Okay.
To get things. So supposing... suppose if you have e to the power of square.
Yeah. Okay.
No, hang on. Oh, I've lost myself. I mean, I'll just get to the point before I think of whether it's worth whether I'm not to explaining it properly. The rule is log A plus log B.
Right. Okay. It's literally that. Okay.
Just taking that on trust for now. We'll come back to powers
Okay. That's fine.
another time. But in the case of log of A times A, then that would expand to
ln A plus ln A.
Yes, log A plus log A, which would simplify to. I mean, we've just got log A and then the same thing again. So we've got. I mean, x plus x would simplify to. Do you see what I'm saying? I'm probably confusing things massively, but just on the principle that x plus x, of course, what's the shorthand for that? Anything plus the
2x.
2x. Yeah.
Oh, 2 ln A.
It just means 2 ln A. Yeah.
Oh, okay. Right. Cool.
Yeah. So log of A squared equals 2 log A, and you could see how that would work for any integer power of A. You'd have log of A cubed would be log of AAA, which would be 3 log, and so on.
Yeah, okay.
So the rule here is that log of A to the power of B is?
Ln of A plus, oh my,
See what the rule here is? We had log of A squared.
Oh, is it B? Sorry, B ln A.
Yeah.
My bad.
Okay. You know, I mean, this principle here does want explaining it. I'll have another go soon enough, because we'll come back to the issue because it's so important. But then if we apply that principle here, we could rewrite log of 3 to the x as?
Log of 3 to the x as, what was it?
On this principle.
Yeah, x ln 3.
Exactly.
Cool.
X log 3. But then that could be rewritten how?
As
on the principle that
as in
no,
in
hang
an
on.
actual
Hang on. Well, that's no problem. That's what we want. That's the form we want to differentiate it in.
right.
Excuse me, I was confused, thinking it was going somewhere else. No, not at all. So we've got 3 to the x is e to this power here.
Okay.
But that is
Okay.
suitable for differentiating with the chain rule.
Okay. Right. Cool.
Yes, that's good. Right. Okay. So let's write it like that. We've got e to the x log 3.
Yeah. And that gets...
which we could write as log 3x, but we wouldn't want, then we'd have to put brackets. So I'm only putting the x before the log 3,
yeah,
so that we don't have to put log 3 in brackets, which wouldn't hurt. It might have been preferable. And now we've got this equation, which we're going to differentiate it implicitly. In other words, even though we haven't got y as an explicit function of x, we're going to differentiate term by term.
Okay, cool. Okay, that's
Okay, tell me where you are. Let me know when.
I am caught up. So, differentiating that will go from when
So
you
how do we
differentiate.
Oh, by the way, you know the basic derivatives apart from the normal power rule. You know that the derivatives. Yes, for example, e to the anything.
Don't you just put what it's to the power of in front?
Yes, e to the x.
Yeah.
Pure and simple does differentiate. It is its own derivative.
Yeah.
That's why it's worth having a number e. Really, it's so remarkable that it is the number which, you know how in general 2 to the power of x, 3 to the power of x, and so on, they look basically like that graph.
Yeah.
And when you differentiate, you get a gradient function. So, for example, here, whatever that looked like, our derivative function here, it's further down, wasn't it? Here,
it was that bit.
Even though it's still not an explicit function of x only. We've got y in there, which is a problem. But anyway, presumably it would have a graph, its own graph, and it would be different to the original graph of y, wouldn't it?
Right. Yeah.
Every time you've got a graph of y against x, you could draw the graph of dy dx against x for that graph.
Okay.
We call that the gradient function of the original function. But e is just the special number which, for an exponential graph, like 2 to the x, 3 to the x, etc., it is its own derivative function.
Right.
It is its own gradient. It's equal to its own derivative.
Okay.
So the gradient, when you look at e to the x, especially, as opposed to just anything to the x, when you look at e to the x, at any point, you say, oh, what's the gradient going to be at that point there? What's the gradient of the tangent at that value of x? Well, it just turns out to be the value of y at that point.
Yeah, okay.
Which is remarkable and useful.
Cool.
Okay. So that does mean that e to the x differentiates to e to the x. But then e to anything differentiates to e to the thing with respect to the thing.
Yeah.
But then we need to apply the chain rule again because it's a composite. So just like here, we said, okay, if y is an inner function, We'll deal with the outer function first and have 6 times the outer function and then times it by the derivative of the inner function. And that's what the chain rule formula is telling you to do.
Okay.
Differentiate with respect to the inner function as though it were just an empty blob, and then multiply by the derivative of the inner function. So we've got e to the power of blob, just because that's e, that's how e behaves. But then we need to multiply by, according to the chain rule, we need to multiply it by du dx.
Which
so
is...
e to the power of blob is dy du.
Yeah, yeah, I mean, ln3 is, the derivative of that is like, it's just that, isn't it?
That's right, because log 3 is a constant, isn't it?
Yeah.
So that's right. That's why I slightly apologise for putting the x before the log 3, if it obscured the fact that log 3 is just a constant multiple of x.
Right, yeah, okay.
And is therefore the value of the derivative of that many x.
Right, okay, cool, yeah.
So we do have here e to the x log 3, because it's the whole of the same inner function. And then this, I've written it too high, haven't I? I want that down there. So that e to the x log 3 times log 3 is the derivative of 3 to the x.
Right, okay, cool.
We could simplify this a little bit as well. We could unpack that a little bit. Let's see how. But
wait, unpack what we're doing right now, what we're looking at right now.
Yeah, we could simply, let's do it at the next stage. We'll leave that like that for now because we're differentiating term by term. The point is, what we've ended up here is just a little bit unnecessarily elaborate. So we can simplify it. But we'll do that in a minute. And we'll carry on differentiating term by term, yeah?
Yeah, yeah, cool. Y is...
Yes. So the next term to differentiate is y, giving, with respect to x,
oh, is it? Oh my word, I've forgotten how to do it. Is that just dy over dx?
That's right.
I think,
just by definition. Yeah. I mean, we don't know what it is yet, but
yeah.
It will help to have an expression, dy dx. I mean, that's
yeah.
what we're trying to find after all.
Yeah.
So we can later on make it the subject of this equation. And then minus, and then I've put some big square brackets here because of the minus sign there, and we're doing the product rule again.
Yeah, okay. So it's
2x times y.
2x is just
2 plus another 2. That's right. And then in this one left alone,
it is.
Do you see what I'm representing with this bubble?
Yeah. It's dy over dx.
Not yet. No, because you have to be careful to differentiate one of them, leave the other alone, and that'll be one product. Do you see what I mean?
Oh, okay. Yeah, and then the other ones.
And then the other way round. So
and the other ones.
So leave this one alone, and it's
2 dy over dx.
It is. I've drawn this a bit cramped, but it is.
Okay.
Notice that I'm differentiating 2x in particular to get 2, and then I'm leaving y alone and writing y.
Yeah, okay.
And then,
then I need to leave
the other way round. So in here,
2x alone.
2x in there.
Oh, and then it's dy over dx, right? Okay,
y
cool.
dx
Yeah.
in there.
Yeah.
So, I mean, you don't need to. I mean, I do. Depending on the kind of problem, you know, I'm fond of diagrams like this, but no, when you're just doing a small product rule like that, you just have to be conscious of differentiating one and not the other, and then again the other way round.
Cool. Nice.
Now we just want to make dy dx the subject here. And we'll find that we can, actually, let's do the before we make that the subject. Because after all, we could remove these brackets here, that's something else. So let's leave the left-hand side on the left-hand side and the right-hand side on the right-hand side. But let's simplify the left-hand side, if we can.
Times so you get
e to the x log 3. Ah, yes. Sorry, I'm scratching my head there, thinking, yes, must simplify e to the x log 3. But where did we get it from? Where did we first write down e to the x log 3?
When we were changing 3 to the power of x.
Oh yeah, and that was 3 to the power. Look at my really silly. That's what I meant, isn't it? Sorry, I had 3x written there, but it was 3 to the power of x. Sorry about that.
Yeah, no.
Yeah, and we wrote that as e to the power of log of 3 to the x, and then we brought the x around the front and wrote that.
Yeah.
But that means we can go all the way in to the extent that the derivative of this just is that times log 3, for the reason that we can see because of the chain rule. But this much here can go back to being 3 to the power of x, can't it?
Yeah.
So on the left-hand side, we can simply write 3 to the power of x times log 3, or log 3 times 3 to the power of x. I'm not sure what's the best way to write that.
Yeah.
Equals dy dx. Now I did need brackets here because of the minus sign. So if we remove the brackets, we've got minus 2y, and then minus also all the
minus. Yeah, everything is negative.
Okay, so collecting dy dx terms on one side and everything else on the other.
Yeah. A second behind, but I get it, so that's not too bad. All right, cool. Yeah, nice. I am caught up.
So what's the next line?
What was the actual question?
Yeah, well,
we just get
find dy dx.
It was just find dy dx. So we
evaluated at a particular point. But...
Oh yeah, of course, right. So we get all the values on one side. So we add 2y to. Oh yeah, got it. Add 2y to the left side.
Yeah.
Okay, cool. Plus 2y.
Try this way this time. Right.
This one should be a bit easier. Minus 2x dy dx.
Oh.
Put minus 2x outside the bracket.
Don't think outside, no. First of all, let's collect them. Let's say we've got dy dx minus 2x.
Yeah.
dy dx. Now, yes, we want to turn two mentions of dy dx into one mention by bringing it out as a factor.
Yeah, dy over dx.
Maybe that's what you meant, but...
Yeah, sorry, I said it the wrong way around though.
So bring dy dx out as a factor, and inside we'll have what?
Minus 2x.
Just minus 2x?
Minus 2x dy dx.
What, inside?
No, wait. Oh, there's a minus there, isn't it? Oh, wait. Oh god, I'm not sure now.
I mean, supposing you were trying to... Yeah?
Is it not just minus 2x?
Not just, is it? Because when you expanded that, what would you have?
Oh, right, you're going to get minus 2x dy dx. Oh, yeah, of course. So it's, you need add... No, just plus 1.
Yes.
Yeah.
So we could put the 1 first and then minus 2x.
Oh yeah, of course, that looks
So if
neater.
you imagine expanding that, you'll get that, won't you?
Cool, yeah, that's me. And then,
And now it can be the subject. dy dx equals.
yeah, dy dx. Cool, 3x ln 3 plus 2y all over 1 minus 2x.
Yeah.
Nice. Cool.
And so what will the gradient be at this particular point?
With coordinates 2 minus 3. Interesting. 3 to the power of 2 ln 3 plus 2 times minus 3. And then,
Oh, have I lost you?
no, I'm here, I'm here.
Oh, good. Oh, sorry.
I just stopped talking
Yeah,
for a second. Don't worry.
Don't worry at all. But that does happen a lot, that people lose their connection.
Oh, okay.
Zoom. So, in which case, just try the same link as before. I'll leave it open on the assumption that that you can get back through it.
I did that in a really messy order. I should probably redo it, but I got minus 1.2. Well, minus 1.3 to one decimal place.
I see. So you put it in a calculator, and you put the same as I've got here. Did you? 1 minus
4.
1 minus 4, so over minus 3, and that comes out to roughly 1.
Have I made a mistake? I think I might have.
I have no idea. Have I not?
No, I haven't.
I'll just check.
I may have done it wrong because I got an error a minute ago.
I suppose we could simplify it a little bit first, couldn't we? We could say that's 2 minus 3 log 3.
Minus 1.295.
2 minus 3. 3. Minus 1.295. Yes, good.
Yeah, that's what I got.
Did they want us to approximate it, I wonder?
Yeah, it wasn't really a...
No. So watch out that, reaching for a calculator is often...
Yeah. Right, so we should... Okay, that's fine. So it is 9 ln 3 minus 6 all over minus 3.
Which will simplify, yeah.
Yeah, I kind of see that now. Minus 6.
And it's, I need an approximate sign there.
And
so that, yeah.
minus 1. Oh, hang on. What did I get? Minus. Hang on. Wait. 2 minus 3 lm3.
Yes.
Is
that what you've got?
2. Oh, that is where I've gone wrong. Don't worry.
Oh, but you did get the same.
Yeah. It was me trying to divide 3 by minus 3 when I didn't need to do anything to it. But the 3 after the ln.
Sure.
That's my fault. This is a constant.
Yeah.
That's okay. That's just a silly little mistake.
Yeah. Fine.
Makes them every now and again.
Right. So, I mean, what's the big picture here? Implicit differentiation is just the nice state of affairs that you can always differentiate term by term.
Yeah.
You don't have to have y as an explicit function of x to get going on it.
No.
Right. And so there's plenty more here. There's never, every one of these is usually worth doing, but on the other hand, so is everything else.
Yeah.
So shall we do this challenge one at the bottom, perhaps?
Yeah, sure. Yeah.
The curve C has implicit equation, as it says, just because, I mean, we won't probably have time to do all of them, but we could do that one now. Oh, and then actually time flies, doesn't it? Yeah, okay, fine.
What time is it?
Well, yeah, I mean, don't worry. I mean, we didn't. It's not that it's just that I didn't notice. Never mind. Right. So they are saying this is a challenge, but to me, so far, I mean, I don't know about A and B, but the equation there looks fairly normal for implicit differentiation.
Yeah.
So we'll go ahead and find dy dx, and then talk about dx dy. Yeah. So, taking it turn by turn, just differentiating with respect to x, because they are initially in part A at any rate, it's with respect to x.
Yeah. Okay. Oh.
So 6x we'll deal with, and then y squared, and then 2xy. Tend to give myself lots of space.
Okay, cool. So
it might be needed. So 6x.
6.
Good. Y squared. This is similar to
2 dy over dx.
Well, no, but that would be the derivative of 2y. Would differentiate to.
Oh, so is it dy over dx?
No, we have got another instance of what happened here with the chain rule.
Right.
Y is the inner function. We'll differentiate with respect to y first of all. Remember how 3y squared became 6y, and then multiplied by the du dx from the formula. In other words, the derivative of the inner function.
2y times dy over dx?
Yes, exactly that. Good.
Cool. That makes more sense.
Now, what kind of rule do we need now? For 2x.
Chain rule. Chain rule, is it product rule?
It's a product, really, more obviously than a composite.
Yeah. When we do.
So.
That is sugar. Hang on. So it is and then we differentiate. Mate. So when you differentiate that, it actually just becomes 2. When you differentiate that, it becomes 2 dy over dx. So the derivative of 2x is 2, and then you leave the y. So the first bit is 2y. Oh yeah, you've written that down. I was just doing that. And then the next bit is So
we did now do it the same
2x,
way around.
2x.
So 2x left alone.
Yeah, and then the next bit is the y, which is dy over dx.
Exactly, yeah.
Cool.
Equals?
Dx equals 2x.
2x, good. And so?
Therefore, okay, we've differentiated all of that. So there are no points when dy equals dx is 0. So minus 2x from both sides.
Sure, yeah. Maybe. I mean, if you're going, well, depending. Shall we leave the dy dx terms on the left-hand side?
Ah, yes. That would be smart. That's what we should be doing first. Okay, so 2y y dy over dx.
And then everything else, like...
There is single negative. Oh no, there's a 2x on that side though, so that's all right. Nice. Okay, cool. I scribbled that out because it was wrong. Yeah, I scribbled that out because it was wrong. Okay, good.
Which bit?
All right. Yeah, I've got the same. And then
Very good.
dy over dx. And then brackets 2y plus 2x.
Yep.
Yeah, then still equals the same thing. And just dy. Cool, yeah. I have 2x minus 2y over minus 6 over 2x plus 2y. Yes. Brilliant. And then we need to prove there were no points on 0.
Right, so show that that's never equal to 0. And now I see what's challenging about it, because I'm not sure I can see that. How we know that that implicit equation there. So it might be an ellipse, I think. Not sure. But anyway, but then it couldn't be. An ellipse would have to have a gradient of 0. Silly me. Right. How do we know that that's never going to be 0? Gosh.
We set it as cos.
Well, I mean, let's try sort of by contradiction. Let's assume that it is. Let's try setting it to 0.
Yeah, that's what I was thinking.
Yeah.
Yes.
But why on earth could? All right. So let's set it to 0. Okay. So if the whole fraction is 0, then what simpler statement can we make?
That 2x that bit on the right equals 0.
Yes, and if the whole fraction is 0, it's always nice that we can just say more simply, if the whole of a fraction is 0, then
the bottom is 0.
Well, the bottom is never 0 because that would make everything explode.
That wouldn't exist.
But for example, well, sorry, to cut to the chase, basically the numerator is going to be 0.
Right, yeah. Oh, yeah, of course, yeah, that makes sense.
So, yeah, so that's always a nice thing with stationary points. You know, if you've differentiated and you're interested in where it's equal to 0, well, if it's a fraction, then we only need to talk about the numerator.
Yeah, okay. Cool.
So if the numerator is equal to 0, that would give us, that would mean that y was what function of x then?
Plus 6, so 2x. 6. Well, I mean, 2x would have to equal 2y plus 6.
Yes, and let's get y in terms of x rather than x in terms of y. I just
okay.
If only for my sake, because I've written it that way. So 2y would be 2x minus 6, wouldn't it?
Minus 6, yeah.
So 1y would be
x minus 3.
And that seems fair enough, but perhaps we can end up showing that if that's the case, it would turn this into a quadratic in x, which has no solutions, which is never equal to 0, yeah?
Yeah. Okay.
So we've got y equals, what was it, 3 minus x?
Yeah. Oh, x minus 3.
Sorry, x minus 3. Well, that'll turn this equation into what? 6x plus
Yeah, we could do that.
minus 3 squared plus 2x times x minus 3 equals x squared. So if we just, and yes, I think that's what's going to happen. So x squared minus 6x plus 9 minus 6x, oh, plus 6x plus 2x squared minus 6x minus x squared. Is this the kind of thing you're getting?
Yeah.
Not to interrupt, you know, there'll be several ways of expanding and so on.
Yeah, minus 6 and minus 12x.
Right, so what have we got?
Minus 2x squared minus 12x plus 9x. Oh, plus 9.
Minus 6x. Plus 9, yeah.
Yeah.
So what's your quadratic, sorry?
2x squared minus 12x.
Oh, only 2x squared.
Where did I go wrong?
Not necessarily.
X squared plus 2x squared minus x squared.
Oh, where's your minus x squared? Oh, here. Yes,
Oh,
quite.
yeah.
My bad. Right. X squared plus 2x squared minus x squared is 2x squared. Quite plainly. Thank you. So 2x squared minus, have you got minus 6x plus 9?
Yeah.
Oh, good.
No, wait, minus 12x. Minus 6x minus 6x. Oh, there was this plus 6x. That's where I've gone wrong. Wait. Yeah, there was a plus 6x that I missed out.
Yes, which I didn't want to write first. I wanted to expand that first, but yes. So yes, 2x squared minus 6x plus 9, is it?
Yeah.
Okay, and now we can answer their first question, can't we? This is a consequence of dy dx being 0, isn't it?
Yeah. And then put it into the calculator and show what it gives you for the answer.
Well, let's not use a calculator, no. Presumably you mean use some kind of algebra button or something, I don't know.
Yeah.
But no, I mean, notice that this statement, dy dx equals 0,
Yeah.
directly implied, or indirectly implied, this quadratic statement.
Yeah.
Now, what's that quadratic saying? That this parabola, whatever it is, this quadratic has got to be a parabola looking like that, hasn't it?
Yeah.
Is equal to 0 and is therefore cutting the x-axis.
Yeah.
Now, how can we show that that is just not happening? This parabola is never cutting the x-axis.
I'm not actually sure.
Well, it would mean that this quadratic equal to 0 has no solutions.
Right, okay.
And how do we show that a quadratic has no solutions? I mean, which part of using the quadratic formula would the calculator throw out as a syntax error?
For 2x squared minus 6x bit?
No, it's this bit here.
Right, okay.
The calculator would have a problem if you wanted it to take the square root of a...
Right, okay, of 6 minus 4 times 2 times 9.
Possibly, yes. You're working out the, what do we call this under the square root? Dis.
It's quadratic.
Well, it's the discriminant. B
Oh,
squared minus
discriminant,
4.
of course. Yeah, I haven't seen this in ages.
Yeah, quite. Yeah, probably not. Yes, but that's what this turned into.
Right.
Assuming that the gradient was going to be 0, that had as a consequence that this quadratic had to be cutting the x-axis, and therefore its
Right.
discriminant, b squared minus 4ac,
Yeah.
must be greater than 0, notice.
Yeah.
You have to have a positive discriminant if you're to get any solutions to the quadratic being equal to 0.
Yeah.
So what's b squared minus 4ac, you were beginning to tell me?
It is 36 minus 4 times 2 times 9, which is 72.
Yeah.
So it's minus 36.
Which is less than 0.
Yeah.
So that answers part A, because we've shown that this quadratic has no solutions.
Yeah. Yeah.
Therefore, and that would have to happen if the gradient were 0. So this means that the gradient can never be 0.
Yeah.
Find the coordinates of the 2 points on C, though, such that dx dy does equal 0. Now, you might have been warned, I would warn you people anyway, to not to be too ready to think of dy dx as a fraction. But sometimes it works as a fraction, and basically, if it does work as a fraction, then you'd expect the gradient given by dx dy
Yeah.
to have what relationship to the original gradient dy dx?
Oh, I kind of went off there. 2x plus 2y over 2x minus 2y minus 6.
Oh, sorry, what's happened? What are you? Where are you?
You said sorry. I stopped paying attention for like a split second because you said
fine,
look at it. I can look at it as a fraction, so I went back to the old fraction and just flipped
Yes, you
it.
have. Well, that was where I was. What I was waffling about while you were doing that was the principle of that. Just recognizing that dx dy will therefore be exactly what you were telling me.
That's fine. And just that's like exactly the same thing, isn't it?
Yeah, same process, but this time it should work, and it should lead to a quadratic which solves for x and allows us to find the 2 points on the curve C.
Numerator equals.
What does that say about the curve C if the reciprocal of the gradient is 0? I mean, in part A, what we've shown is that whatever curve is implied here has no horizontal tangents.
Right. Oh, okay. Yeah.
So this is going to be about finding what features of the curve?
A turning point.
Well, the turning points are what we call points with a horizontal tangent.
Yeah, I've got wrong one. Just so.
It's here where we flipped the gradient and put it equal.
So the negative. No, that's stupid.
Negative reciprocal is for perpendicular gradients, isn't it? Yeah.
Yeah. Yeah, that's why I said it.
Not stupid, just different. Yeah.
No, I'm not sure.
But well, connected with that, I mean, perpendicular gradients have to be negative and reciprocal. Inverse gradients are the reciprocal of each other. So I mean, what you found here is the reciprocal of that gradient.
Right. Okay.
Now we couldn't find any of that gradient which were horizontal, equal to 0. Okay. But now that we flipped it, I mean, yes, you're right, actually. Equal 0 is going to be the only point at which the reciprocal, if it makes sense.
When x equals y. Wait, no, that's crazy talk.
What's crazy? Sorry?
I said x equals y, but it doesn't. If you did
yes,
2x equals minus 2y, x equals minus y, or when minus x equals y.
Exactly. Y equals minus x. That's the way we're going to transform the original equation this time and get a quadratic, which hopefully does solve for x, and we can find out where. Now, all I was trying to get clear was when we do that, when we found it, 2 points where dx dy equals 0, those are going to be points where what is happening on the curve? I mean, I haven't asked about this, but we might as well just be clear that dy dx is 0 when the tangent is horizontal. Dx dy is 0 when the tangent is?
Like perfectly diagonal, 45-degree angle? I don't know, that was a guess.
Right, okay. But, well, a reflection of a horizontal line in y equals x, because it will be the gradient of the inverse function. And the reflection of a horizontal line in that line is? What's the reflection of the x-axis in the line y equals x?
Y-axis.
The y-axis.
Right, okay, cool.
So dy dx is 0 for horizontal tangents, which we call stationary points.
Okay.
But dx dy will be 0 at?
Y-axis points. Wait.
Well, vertical tangents, yeah.
Yeah, okay.
Points with a vertical tangent, yeah. So how's that quadratic coming out this time? So 6x.
2x plus 2y equals 0, which...
6x, where is it? Plus 2. What? Plus minus x squared.
And then, so you get, oh, that was what I had to do.
2xy.
Put all the x values in.
Plus 2x times minus x equals x squared. Right. Oh, right. So there's x squared. Oh, no. Right. So 6x minus 2x squared. Is that right? 0?
Yeah. That equals that. That equals. Minus x. Which is minus x squared. And then that is minus 2x squared. Yeah, and then that is also wait, so 6x minus x squared.
Oh, minus just x squared. I had minus 2x squared.
No, don't worry, I'm going a bit slower here. Minus 2x squared minus x squared. I've got minus 4x squared. I don't know if I've done something wrong. Because
Not at all. No. What on earth was I doing? Oh no, hang on. So have you got this line here? 6x plus the square of minus x plus 2x times minus x equals x squared.
yeah.
Right. So these two cancel, don't they?
Which two? The x squared, because you'll take
Yeah, I think that's right.
You've got minus x squared on one side, you've got x squared on the other.
Well,
So
it's
you
the
have
square of minus x, don't forget.
the square
This
of
was y
minus.
squared is going to be the square of y is going to be the square of minus x, which is plus x squared.
Okay. I just move the x squared to the other side, which is minus x squared.
So which x squared? Which one did
The
you move?
one on the right. I took away minus x squared from both sides to get it to equal 0, and then I just had another minus x squared.
What line? What's the closest you've got to this line? Just read your line out. The one that
No,
starts.
I have 6x plus minus x squared
Yes,
plus
but when
2x.
you write minus x squared, are you writing it like this? Oh, whoops.
Oh, because it's like that. Okay.
That is
Okay.
ambiguous, you see. You need those brackets.
Yeah. All right, cool. Yeah, minus x times minus x. Minus x squared. Got it.
Great.
Cool.
So 3
Yeah.
minus x. So the x values, let's go. But that's where you get, is it?
Yeah.
So
Yeah.
these are the 2 points with a vertical gradient.
Yes. 3 and 0 is the x points. Yeah, and then you put it back in and you can get the y values. Yeah. Cool. Cool. Yeah.
What is the gradient at those 2 points, by the way?
The gradient of those 2 points. Well, it's at the point dx dy.
Where
Wait,
dx dy equals 0.
wasn't it 0? Yeah.
Sorry?
0.
Dx dy was 0, which meant that the tangent lines would be what at those 2 points?
But like that. But what do you call it? Did I write it vertical? Well, no, it's like vertical, but it's not because it's like horizontally vertical. I'm not sure. I'm a bit
No,
lost.
they are literally vertical points on the curve.
Yeah. Oh, yeah. Of course they are because it's when. Yeah. Yeah. Of course they are because it's when they. Yeah. Yeah. Because the gradient is changing.
But I see what you mean by horizontally, vertically horizontal. Absolutely. I mean, they haven't. If they hadn't done it like that and say find the points where the reciprocal of the gradient is 0.
Right.
They would have had to have said find the 2 points on the curve where the gradient is what value?
Not 0.
Where dy dx equals what? What does dy dx equal?
The gradient.
Yes, the gradient. And what is the gradient going? What's the value of the gradient going to be at these 2 points, which are vertical?
It's the other way up. Oh yeah, of course, because we were never doing dy over dx, we're doing dx over dy.
Yeah, yeah. Which would be the gradient.
So it's like 1. Oh, it's the other way around. So it's 1 over. It's like 1/3, but you have to write the points out. So.
I'm lost. I'm not sure.
No.
I just thought before leaving this, we ought to agree what the questions were asking us about the curve. It did turn out that there's no stationary points.
Yeah.
No points with a horizontal tangent. That just isn't happening. But whatever else is happening, there are a couple of points with, I suppose, if it's a function. No, they've got turning points. So it must be increasing or decreasing, you see.
Right. Okay.
All the way. But there are a couple of points which are where the gradient is what? We would say the tangent is vertical here.
Right. Yeah. Okay.
So perhaps the points were here.
The gradient just. It's like 1, but it's not because it's divided by 0.
That's right. The
Yeah. Okay,
gradient
no.
is divided by 0, yes, which earlier on I said couldn't happen.
Yeah. It's the other way up.
So what happens when a fraction is divided by 0?
Well, it's 0. You can't do anything with it.
Well, no, because when you divide by less and less, have you noticed what happens? You know, if you
Oh yeah, it slowly decreases in height, per se.
does it? If you divide by half, that's like
Yeah.
timesing by what?
Oh, 2.
Yeah. Divide by a tenth. So 1 over a tenth is?
1 over a tenth is timesing by 10.
So 1 over a millionth and so on. 1 over a millionth is a million.
Oh, so it gets bigger.
So as the denominator gets closer and closer to 0.
Yeah, it increases in size.
Yes.
Which is why it goes like this. Okay, yes.
Which is why we're not really allowed to talk about the gradient of a vertical at a vertical point. We're not really allowed to talk about the gradient of a vertical line because the value of that gradient would be what?
0.
No, the denominator would be 0, and therefore the value of the fraction would be. Where was this heading? If we do 1 over a million, we get a million.
It was getting bigger. The gradient was getting bigger.
Yeah.
Yeah. So it'd be like too big. I don't know.
Too big. Yeah. In other words, I mean, when this gets to completely 0,
yeah,
you're dividing those by so little that the size of the fraction must be
infinite.
Exactly. Which we have to be fussy about in maths, and otherwise,
yeah.
You know, so we say actually the function is not actually defined. The gradient function is not defined at those values. And we have to go to the length of just saying, well, the inverse function is horizontal at that point.
Right. Okay, cool.
I mean, we can say that the point on the graph is vertical at that point. We're just not allowed to evaluate the gradient function because it would have to evaluate to infinity, which we just don't allow.
Right, okay, cool.
Because infinity is not a number. You know, you've heard that kind of doctrine. That's all I'm getting at.
Yeah, no, that does make sense. A gradient that is infinite. Cool, cool, cool.